You ever look up at a massive passenger jet and just wonder, how in the world does that giant metal tube not just fall apart in midair? I mean, it's battling insane turbulence, the pressure changes, the pure forces of flight. Well, today we're going to peel back the skin and look at the invisible science that keeps these amazing machines flying safely.
So this is the big one. This is the central challenge for every aerospace engineer. How do you design this massive, complex structure made of literally countless parts and make sure it can handle every single force it's ever gonna face? The answer? Well, it's a whole field of study called structural analysis.
Here's the thing. You can't just solve for the whole aircraft in one go. It's way too complex. It would be impossible. So engineers have this brilliant strategy. Instead of looking at the big picture, they zoom way in. They break the problem down and analyze the forces acting on one tiny, infinitesimally small piece of the material itself.
All right, Section 1, the engineer's central question. This really gets to the heart of it. To figure out how this massive, complex machine behaves, engineers have to completely shift their perspective. They have to go from the macro, the whole plane, all the way down to the micro. Which brings us right to Section 2, forces from within. See, to understand how a material stops itself from breaking, we have to look at the invisible battle happening inside the material. And that's where we meet our first big concept, stress. And when I say tiny, I mean tiny. We're zooming all the way down to this, a single infinitesimally small cube of material. You can think of this little cube as our laboratory, because believe it or not, everything that happens to the entire aircraft structure, it can all be understood by figuring out what's happening to millions and millions of these tiny cubes. So, our first key concept is stress. What is it, really? Well, imagine a game of tug of war. Stress is that feeling of tension inside the rope. It's not the people pulling, it's the rope's own internal forces fighting back against being pulled apart. It's the material's resistance, and we measure it as force over a specific area. And of course, engineers have a precise way to calculate this. The fundamental definition is stress equals dN over dA. Now, don't let the letters scare you. It just means you're looking at a tiny bit of internal force, that's the dN, acting over a tiny little bit of area, the dA. This formula is the key. It lets engineers pinpoint the exact intensity of that internal force at any spot in the material. Okay, so applying stress creates this internal battle inside the material. But what's the visible results? What actually happens to the material because of this fight? Well, that brings us to Section 3, the shape of strain. This is all about measuring how the material actually changes shape or deforms. Think about stretching a rubber band. Strain is just a measure of how much longer that rubber band gets compared to how long it was to begin with. It's all about the relative change in shape. Because it's a ratio, like change in length divided by original length, it actually has no units. It's just a number. It is the physical, measurable consequence of that internal stress. Really, the simplest way to remember this is just cause and effect. It's that simple. Stress is the cause. That's the internal force. Strain is the effect. That's the deformation you can see and measure. And an aerospace engineer's entire job, in a way, is to understand and manage this critical relationship. All right, on to Section 4, a material's personality. This is where it gets really interesting, because not all materials are created equal, right? Every single material responds to stress in its own unique way. And engineers have this amazing tool to capture that unique behavior. It's called a stress-strain curve. So let's take steel and aluminum alloys, for example. Both are super common in airplanes, but they have totally different personalities. We can see this in a couple of key numbers. First, there's Young's modulus, which we call E. Think of this as the material's stiffness. A higher E means it's stiffer. It takes a lot more force to get it to deform. Then there's Poisson's ratio, V. This cool little number tells you how much the material thins out sideways when you stretch it long ways. These numbers aren't just trivia. They're absolutely critical for designing anything that flies. So knowing a material's personality is one thing, but the real million-dollar question is, when will it break? That's what it all comes down to. And this leads us to Section 5, predicting the breaking point. Engineers have some incredible tools for this, and a classic one is called Moore's Circle. It's basically a graphical calculator that helps them find the absolute maximum stress a material is feeling, no matter how complex the forces are. And this is why all this math and theory matters so much. Getting this right Understanding these maximum stresses is literally the difference between a wing that flexes safely in turbulence, just like it was designed to do, and a wing that snaps. The stakes couldn't be higher. But here's a twist. Failure isn't always about one single massive force. Sometimes the danger is more subtle. It can come from millions of smaller, repeated loads over time. You've probably heard of it. It's called metal fatigue. This chart, called an SN curve, is the playbook for fighting it. It tells you, for a specific level of stress, exactly how many cycles, how many takeoffs, how much turbulence a material like this aluminum can handle before it's expected to fail. This is how engineers determine the safe lifespan of an entire airplane.
Okay, so we've gotten really good at understanding what's happening inside one single microscopic cube. But how on earth do you apply that knowledge to an entire massive airplane? How do you scale it up? Well, that's what our final section is all about, from cube to cockpit. The magic here is a process called the finite element method, or FEM for short. Basically, a powerful computer takes the entire aircraft structure and digitally slices it up into a mesh made of thousands, sometimes millions of these little elements, or cubes. Then it gets to work. It applies all the known forces of flight and calculates the stress and strain for every single element. It's like doing our tiny cube analysis millions of times in the blink of an eye. And when it's done, it stitches all those millions of individual results together. And what you get is the complete picture. The computer takes all those calculations and turns them into a visual map, kind of like a weather map, but for stress. Suddenly, those invisible forces are made totally visible. The different colors show where the stress is highest and lowest, and this is the game changer. Engineers can instantly see the hot spots, the areas under the most stress, and they can go back and strengthen the design exactly where it's needed most. So let's just pull this all together real quick. What are the key takeaways? Stress is the internal force fighting back. Strain is the physical change in shape, the properties of the material itself, its personality. Link the two. Engineers use special tools to predict when a part will fail from a single big force or from fatigue over time. And finally, amazing computer methods like FEM let them take all that tiny cube knowledge and scale it up to build a safe entire aircraft.
So the next time you're on a flight and you look out the window and see that wing flexing up and down in the turbulence, you'll know it's not just a random piece of metal flapping around. You'll know it's an incredibly complex, precisely analyzed structure, doing exactly what it was designed to do. And it makes you think, doesn't it? When you look around at a bridge, a skyscraper, or even a car, what's the hidden margin of safety, the invisible engineering that you now see everywhere?